Okay. Okay. Great. Okay. Yeah, the title's not there, so it's a little unfair to Louise. So first, let me uh, thank you all for coming and being here to hear about some of what I've been working on. A lot of it, all of what I'll talk about, actually, I've been doing with Louise in the last couple of years. I've been spending a sabbatical semester here, and it's been really wonderful seeing so many old friends and making some new friends and learning a lot of physics while I've been here, and I've really been enjoying my time. Um, so I just want to start with a sort of motivation page, sort of what got us thinking. This is not working. So um, maybe this works. Okay. All right. So, what got us thinking about the topic that I want to tell you about today, and there's a great deal of expertise in this general area of van der Waals materials right here in this room. Um, and it's an amazing kind of universe that's been realized in the last 10 years or a little bit more, that there's this whole family of layered materials that you can do many different things with. So, for example, back in 2007, we learned about Moiré lattices that you get from taking, let's say, two layers of graphene and twisting them and laying them upon one another. Um, but this really goes further than just the Moiré lattices. You can take different types of materials and put them together and think about engineering various band structures, doing things that might be practical, maybe get things with useful optoelectronic properties. There's all kinds of things that people are thinking about. These are actually kind of older review articles at this point, but they did actually kind of anticipate many of the systems that people are going to be looking at. So in this sort of world of possibilities, particularly in the heterostructures, we started thinking about what would happen when you have different materials on top of each other that might have different Berry's curvatures. So electrons in the systems may be moving around in a situation where they have to deal with more than one Berry's curvature at the same time. And so that's sort of the beginning of what we start to think about. We want to know what would happen in such situations. And a concept that we kind of came across as we were figuring this out is one that we've given a name. We call it quantum geometric dipole. And in particular, it's relevant to collective modes of these systems that can be described by two-body excitations. And I'm going to go over this actually in some detail. So I'm going to try to be clear about what we've actually done. Okay, so once we've kind of defined this, I want to talk about two applications that we've worked on. One is excitons in mostly bilayer structures, and we'll see that by looking at these excitons and their semi-classical dynamics, you can see this quantum geometric dipole give a signature to its presence. We also looked at plasmons in a couple of different settings, a regular sort of two-dimensional electron gas and also in a one-dimensional quantum wire. And what we're going to see is that one of the main physical attributes, physical consequences of having this quantum geometric dipole is a skew scattering effect that I'll describe. So as Louise said, here in a sort of younger, happier times, is our friend here, and my student Jin Liu, who just actually defended his thesis, really did the heavy lifting and most of the calculations. And now there's a few papers at this point on what I'm going to talk about. Okay, so I actually want to start with a very basic slide here about Berry's curvatures because I want to be very clear about what we do that's different than what's usually done. So to be sort of starting with the simplest systems, we can just imagine some two-dimensional band structure. And we'll just think about single particle electronic states in this setting. So we learned back in our beginning of graduate school or even as undergraduates about block states. They're plane waves times some periodic wave function. And the first step that you follow in figuring out about these about Berry's curvature is stripping off this plane wave part and then writing down an eigenvalue equation just for the periodic part. Okay, and we can think of this equation as a set of equations that are parameterized by a two-dimensional wave vector by a two-dimensional set of parameters. And the idea here is the way we want to think about geometry is that these u's represent some kind of generalized vectors, and they move around in this parameter space. When I change my wave vector, I'm actually changing where I'm looking at these wave functions. And the geometry then you begin to think about is how those wave functions change as you move through that parameter space. And so this quantity is known as the Berry connection. You can see it's an overlap of the wave function with how it's changed as you move through the parameter space. Of course, the problem with this this quantity is that it's not gauge invariant, so there's nothing that's directly measurable that you can quantify directly in terms of A. But there are various things you can construct from it that are measurable. So, for example, if you take this, take the Berry connection and integrate it over a closed loop, that is something that's gauge invariant, and there are various types of quantum interference experiments that you can cook up that will in some way actually measure this phase that you pick up in a closed loop. The other one that's very heavily studied is the Berry curvature. You take another derivative, basically a curl of this Berry connection, and this is basically a kind of generalization of a two-dimensional Gaussian curvature, but in this more generalized space of vectors. Okay. Now the Berry curvature is also something that has measurable consequences. In particular, when you look at the electron dynamics, you find this term over here, which I did not learn about when I was a graduate student, when I was doing my introductory condensed matter physics. It was known, but it wasn't thought to be particularly important until more recent times. It's what we call the anomalous velocity, and it has a lot of important consequences in terms of the dynamics of electrons. One very interesting and important application is the quantum Hall effect. So if we imagine that the problem we're solving is just electrons in magnetic field, we have Landau levels, and this is the problem that Thales actually worked with coworkers and was part of the reason he won the Nobel Prize. So if you actually basically integrate up this contribution from the velocity written as a current, you can basically figure out the total current that's carried by a filled Landau level, and this turns out to be to give you the Hall conductivity of the system when you're in the presence of an electric field. And again, Thales taught us that this is actually a quantized value. But there are sort of more recent ways about places where people think about just the same kind of physics. For example, if you have a Dirac Hamiltonian with a gap, you can imagine putting your chemical potential down here and then compute the Hall effect. Using this term over here, you'll discover it's non-zero as long as your Fermi energy is going through the band. When you get into a gap, you actually get a quantized anomalous Hall effect. And then if you go further up in your Fermi energy so that you start to fill this band, then the currents from the two bands will start to cancel. The anomalous Hall effect will start to go away. Okay, so this is showing us that there's more general applications of this dynamics due to the Berry's curvature. Now, just to really convince you it's real, in case you didn't think it was. So this is a nice experiment, or one I think is very nice, from Paul McEwen's lab, where they really very directly showed the Hall effect coming from Berry's curvature. And the way they did this is by shining circularly polarized light on a TMD material. It's a MOS2. The thing that's nice about circularly polarized light is that it will make electron hole pairs will create electron hole pairs in sort of unequally in the two valleys. And for the two valleys turn out to have different Berry's curvatures, so that when you do this imbalance between valleys, you actually end up with a situation where the Berry's curvature, effects of Berry's curvature are not canceling against the two from the carriers in the two valleys. So what they showed is that when they created their carriers in this way and put an electric field across the sample, they actually get a Hall effect. And they're showing that over here. And the sense of that Hall effect actually changes depending on whether you have left-handed or right-handed circularly polarized light. So that's the two different diagonal lines here. The two different senses of circularly polarized light. And if you use linearly polarized light, you don't see an effect. Right? So you really need to do something it's ultimately time reversal symmetry breaking, something that will pick out one valley over the other. This is not a bilayer. This is a single. I don't actually. I think this must have been a bilayer where the curvature was 0, where the Berry curvature was 0. Yeah. I've forgotten about that blue line, right? Yeah. Okay. All right, so we're starting to get into what we were focusing on is what happens when we have a situation where there's more than one Berry's curvature for the electrons to deal with. And a very natural sort of first type of system to think about, a first type of electronic state to think about is an exciton state where you have a bound particle-hole pair. And in particular, we were thinking about these kinds of heterobilayers where you could have interlayer excitons. So exciton, again, is kind of like a hydrogen atom. It's kind of a positive charge in one band, a negative charge in another band, which forms a bound state. And there are lots of types of materials and experiments where you can actually form that bound state across the gap of a bilayer. Okay, and you can make this tunneling between the two layers essentially negligible so that there'll be an electron in one layer and a hole in the other, and they basically are forced to live in one layer or the other. So one thing that's nice about this setting is that you can imagine many different materials for which you can make these bilayers and sort of look at different Berry's curvatures that the electrons and holes might be living in the materials. And moreover, this system is very nice because it has some nice experimental properties. One is that the binding between the electron and hole tends to be very large in two-dimensional systems in general, and in these bilayers in particular. So that means that you can detect them through photoluminescence rather well. The photoluminescence line from a recombining particle hole in an exciton state is well separated from the continuum. So their photoluminescence lines are rather easy to see. Another nice point is that because they're spatially separated, and if that, again, that tunneling is very, very small, this electron hole pair can live for a very long time. Okay, so you can actually have time to look at dynamics, for example, of the electron hole pair before they recombine. The other thing that we wanted to take into consideration is the possibility of putting a magnetic field perpendicular to the bilayer. So that in particular allows you to think about what happens if graphene is one of your layers in the system, because once we put in a magnetic field, the spectrum breaks up into Landau levels. You get gaps between the Landau levels, and it's very important if you're talking about an exciton that you have to have an insulating system. We need to be able to put our chemical potential into a gap region if we want to talk about excitons. Exciton is a two-body state, and we want to do quantum geometry on the exciton, so we're going to need to deal with wave functions. And you can actually pretty much write down wave functions in a nice way for an exciton. So we're going to write it as a function of a particle and a hole coordinate. And you can basically think of it as a variational wave function. So this is written in a form where we've separated out the kind of plane wave piece for the average position of our exciton, and then there's sort of an internal difference coordinate for the particle and hole. And then you build the state by taking tensor products of the electron states and the hole states in such a situation where basically the total momentum of the particle hole pairs is capital K. And then you take all possible linear combinations of this tensor product that have the right momentum. And then this coefficient here becomes a variational parameter. And so you look for basically stationary solutions of the Schrödinger equation set up as a variational problem. Okay. All right, so now if we want to follow our noses and kind of talk about Berry's curvature for these types of states, the first thing you want to do is strip off that plane wave piece like I showed you in the earlier slides. All right, so that's of course what people did when they first started thinking about these types of Berry's curvatures. But as we start to work on it, particularly in the heterostructures where the environments for the electrons hold could be quite different, it started to not be so obvious that this was the right way to strip off the plane wave part. We were a bit confused about this for a while. And it's actually important to think about what you're really doing when you strip off this plane wave piece. So this is supposed to be my one sort of math type slide. So over here, this torus here is a representation of the two-dimensional parameter space, the wave vector space that we're moving in. So actually it should have been K, not Q, I realize now. So this should be actually Kx and Qx, showing my two parameters for the wave functions. And then we have our wave functions that are functions of momentum. And the way you're supposed to think about this is that states at different momenta actually live in very different spaces. They live in spaces that we often call tangent spaces. And for us, the vectors are actually states, eigenstates of the Hamiltonian, labeled by these momenta. Now, if we wanted to talk about something like a Berry's connection, where you take a derivative, you actually run into a problem if you wanted to directly, let's say, take the derivative of this and the overlap with that state. That actually doesn't make any sense. It's kind of like trying to compare apples and oranges, right? Because these these vectors live in different spaces. And indeed, if you try to directly do what I just said, build a connection directly from the wave function, it wouldn't make any sense, because you'd find that if you take the difference and take the difference between the q's to be small, that the limit is not smooth. You can't really do that derivative. So all this is to say that in order to take differences or derivatives, we need to bring our vectors onto a common plane. And that is actually what you're doing when you strip off that plane wave piece. You're putting the vectors into some plane so that you can compare them. So you could look at derivatives and differences and things like that. So the reason for reminding you of this sort of mathematics is that once we start looking at many body states, even just two body states, the kind of set of possibilities that we have for this mapping from the tangent spaces into a common space becomes much larger than what we had when we were just talking about the single particle problem. So this is saying that we really can define many different kinds of connections. And that's actually what we sort of recognized and started to do. So one way to do this is to define a family of connections with a parameter alpha, which is just a real number, right? So basically what I can do is place kind of the weight for the plane wave in the particle, or rather in the hole or the particle, the way we've labeled this. We could really choose how much weight I want to put on the two particles. So I have a set of possible connections that are labeled by this alpha here. And there are two that turned out to be very useful for us. One in which we put all the weight on the hole, and one in which we put all the weight on the electron. So I'm kind of associating the plane wave momentum part with either the hole or the electron. And the reason this is useful is because if I take a difference of these two objects, this actually turns out to be, again, a gauge invariant quantity. And it's very easy to show that it's directly related to the dipole moment of your excitation. So this R1 minus R2 is the difference coordinate. It's the distance between your particle and your hole. Yeah. It's fixing if I set alpha to 0, for example, I'm putting all the weight for the plane wave on the electron. R2 for us is the electron, right? Well, I'm not localizing it, right? Because this is the wave function. I have a probability amplitude distribution for the electron and hole to be at different places. But I'm saying as I change the position of the electron, I'm going to pick up this wave vector. Right? I'm going to pick up this phase, right? And I'm saying moving, even if I move R1 and R2 together, I'm really associating the phase with just where R2 is. Okay? Yeah. Well, I'm not sure what you mean by single part. You mean go back to the non-interacting? Right. So so there's no simple connection, right? Because you have that C, and that C has K dependence in it, right? So those form part of it, but then there's more, right? When you're calculating it, there's a contribution from the C as well. Okay. Okay. So as I said, this is obviously because this is something that's very physical. This difference here is a gauge invariant quantity. And so because it comes from this sort of quantum geometric way of thinking about things, we've given it, that's where we decided to give it its own name. So we call it this quantum geometric dipole. Okay. All right, so there's an application that's been known for many years. Actually, I don't have a full list here. I think it's Lerner and Lozovic actually were the first ones to figure this out in 1979. I've learned that for some reason it didn't make it onto the slide here. But anyway, this is the problem of magnetoexcitons. So this is a two-dimensional electron gas, again, with a perpendicular magnetic field. We're in the quantum Hall regime, even if back in 1979 they didn't call it that. You can think about collective modes where if you put your chemical potential between Landau levels and now you excite an electron from one Landau level to the first unoccupied Landau level, now we can have a bound particle hole pair, just like I was talking about for the heterostructures, but now between Landau levels. Okay, so this, a long time ago, the energies and various properties of these kinds of excitations were figured out for the two-dimensional electron gas. This is from my own thesis advisor's work from 1984. This picture over here is this is actually contributions to the energy as a function of wave vector. The omega c part is actually missing from this. I think the full energy is omega c plus this solid line. Okay, and one of the things that's pointed out in the Lerner and Lozovic in '79, and also by Callan and Halperin, is that this excitation actually has a dipole moment associated with it, and they actually wrote down this expression for it with a sort of constant over here. So you see that the dipole moment is perpendicular to the wave vector, and this constant over here is this magnetic length, which turns out to play an important role and will be interesting for what I have to say a couple of slides down. So it's actually quite easy to sort of understand why there should be a dipole moment in this excitation. So we have a particle on a hole moving through the plane. It's got some momentum. And because of that motion, if we're in a magnetic field, we know we have a Lorentz force. Right? And so that Lorentz force, for example, might, it should be set up such that the Lorentz force sort of pushes, let's say, the electron out and the hole out away from each other. But then we have the attraction, right, from the Coulomb interaction that keeps them together. And those two forces balance each other out. All right, and so that's how we get a stable excitation out of this particle hole pair. So, okay, so that being said, so they computed this. So we went ahead and computed this with this formalism that we start to develop, and it indeed gives you the right answer as it should if we didn't make any mistakes along the way. So it's a known result, but we get a little new insight that this is something we can understand in a quantum geometric way. Okay, so this is sort of the first not I don't want to say non-trivial, but first sort of calculation where something that isn't already known is being done. So here we have, if you want, we can think of this as band structures for two layers, a electron and hole band. And you excite your electron from one hole band into a different electron band. It actually turns out to be important that there's some difference between these two, let's say these two layers, these two band structures. So the delta here is the gap for each of these, and the v is the velocity of the particles. Again, we're taking a very simple Hamiltonian, just a gapped Dirac Hamiltonian. You can work this almost analytically. Yeah. Oh, no. The last slide, you mean? Or? No, they have the same Barry's curvature. So this is a case, right, they have the same Barry's curvature. Every Landau level is really just a flat Barry's curvature that adds up to e squared, adds up to 1 when you do the Chern number. Mm-hmm. Yeah. Okay. Okay. Okay, so you can almost do this analytically. At the end, there's an integral that has to be done numerically, but you can compute this quantum geometric dipole for this type of excitation, and the result is over here. Very interestingly, you see it starts out linearly, and it's also perpendicular to the momenta, and that seems to be the sort of a common thing that we find pretty much all the time, is that this dipole moment is always perpendicular to the momentum in these two-dimensional systems. Okay, starts out that way, so kind of looks like the magnetic field result, but then it starts to get more structure in it. It actually even changes sign as the momentum gets large. Eventually, when you go to large momentum, it goes away, which is a difference from what you get in the magnetic field case. The other thing you can look at is a form of Barry's curvature that applies to these two-body excitations. It's in particular, we're looking at the sum of the two Barry's curvatures and taking the curl. And this is not totally arbitrary. There's a reason for taking this to be your effective Barry's curvature for the exciton as a whole. And I'll show you that right now, I think. Okay. And it basically comes in when you look at the semi-classical dynamics. So now you can ask what happens if you put in electric fields to try to push these excitons around. You can kind of follow a wave packet formalism that's due to Chan-Nu. That's what we did to find what these equations of motions are. In the case of uniform electric fields, you get something that's really simple. So the r plus here is kind of the center coordinate for your particle and your hole. And then we'll have the momentum as a degree of freedom, and the separation r1 minus r2 is actually tied to that momentum through this quantum geometric dipole. Okay, so you don't have the difference coordinate as a separate degree of freedom from this center, if you want, from the Kc, from the momentum of the exciton. Okay, and so the pieces, most of what's here should be familiar. This is more or less the center coordinate. It's time derivative. Then we have a part that excuse me, is just like that anomalous velocity that I showed you before, but the omega here is exactly what I showed you on the last slide for our effective Berry's curvature. So it's not just anything. Then you have the dispersion, the gradient of the dispersion, just like we have for the single particle dynamics. And the qualitatively new term is one that kind of makes sense. It's kind of the energy that you get of the dipole moment in the total electric field. So the E plus here is the total electric field in the system. I'm allowing the possibility that the two layers have different electric fields. Since I've turned off any kind of tunneling between them, I'm allowed to do that. Okay, so this is the extra term that comes in, and it gives an interesting phenomenon. Okay, in particular, if I look at the situation where these electric fields are the same, you'll find that this exciton develops a drift velocity perpendicular to the electric field. All right, that happens even in the Magnetoexcitation case, and there it's actually quite easy to understand why it happens. If you put in an electric field in there in the Magnetoexcitation case, you could always go into a frame of reference where that electric field is zero, right? We can make a Lorentz boost, and if that electric field is not there, then the exciton should not move. The exciton in that frame of reference should be stationary, and so we can understand the drift as really being a consequence of the Lorentz invariance of the system. Okay, so that L squared that I showed you that went in front of that was sort of the working coefficient of the size of your dipole moment, that's exactly what you need for the system to obey Lorentz invariance. Okay, so that's not an accident. Yes, Elsa? For the magnetoexcitons, I'm specifically talking about this problem. All right. Whoops, went past that. Okay. Yeah. I'm not sure if I call that start shift or not. I mean, it is a dipole moment, right? Well, it's the same kind of coupling. Maybe yes. It's the same energetic coupling. Yeah. Okay. All right, so we can understand why there should be drift in the presence of an electric field. So you could look for this effect now in the situation where there's no magnetic field, where it's not so obvious why this would happen. So for example, we could look at that bilayer TMD, and we did some estimates. And one of the things that we found was that this drift would actually be kind of a small effect in a zero magnetic field in some typical bilayer TMD. And the reason for this is basically that same sort of positive effect, the binding energy of the excitons in these kinds of bilayers is very strong, right? So that's a positive for being able to observe things by photoluminescence, but for looking for this kind of phenomenon, that turns out to be a negative because the strong binding means the excitons are small. So their dipole moment is small, and the drift velocity you get is small. And it was not really possible for us to convince ourselves that the exciton could go far enough, given sort of what we understood be the current constraints on resolution and time-resolved experiments. We couldn't really convince ourselves that excitons could go far enough before they'd recombine, because that in these cases the dipole moment is quite small. So there's an interesting way out though here, and that is to put in the magnetic field into the problem, into the bilayer, the hetero-bilayer problem, because that introduces a new length scale. It introduces the magnetic length as a length scale, which is much bigger than this interlayer distance. And the size of your excitons a strong enough magnetic field will get much larger, and thereby your dipole moment gets much larger. And this can be a couple of orders of magnitude bigger. This can be, quite a big effect. And so if you look for the drift velocity in this kind of geometry, um, um, if you look for the drift velocity by applying an electric field, what you're really looking for now is a deviations from Lorentz invariance. You're looking for how far this velocity differs from what it would be without without the Barry's curvature and without the sort of quantum geometry of the intrinsic quantum geometry of the system. And it turns out that intrinsic quantum geometry really gives you a fairly large correction. So these are sort of the corrections that Jin Liu computed for. This was an MOS2, graphene MOS2 bilayer in this case, in a magnetic field. And they're basically of order 1. You get something where the dipole is changing by 50% or 70%. And so that's a big effect. This, we think, is something that really should be, in principle, measurable. Okay. So, so there are a couple other things we came across that we thought were interesting to think about, which we haven't really done much to push forward yet at this point. One is actually we found that some of these hetero bilayers actually will give you an exciton dispersion where the the minimum of the energy of the exciton is not at k equals 0, but at some finite momentum. So that's an interesting situation to consider, exciton condensation, right? If you can make a lot of excitons in this kind of structure, maybe you can get condensation into a finite momentum. So, for example, does that mean that this kind of condensate could it end up having a macroscopic dipole moment associated with it, because all the excitons would, in principle, have the same dipole moment. Another interesting thing is that I didn't really talk about is what happens when we allow the electric fields to be different in the two layers. So in this situation, the momentum actually grows, and remember, the size of your exciton will ultimately grow if your momentum grows. And this means that we could think about pulling particles and holes apart by putting different electric fields in the two layers. So that raises the possibility of getting a photocurrent that's perpendicular to your electric fields. Maybe there could be some kind of dissipationless photocurrent associated with this. So this is nothing that is still on the to-do list, but I think is worth carrying through. All right, I'm about to switch to plasmons for the last 10 minutes or 15 minutes, whatever I have left. Does anyone want to ask anything about the excitons? Yeah, Fernando. Yeah, so the Lorentz invariance, what's relevant is this particular coefficient. This is not just anything. It has to be this coefficient if the system is Lorentz invariant. Okay. That's correct. So in these sort of systems, you're doing everything I've talked about are continuum approximations. I haven't actually gone to the lattice scale. And in this case, you're taking a quadratic Hamiltonian, right? So it's free electrons with renormalized mass, Lorentz invariant. Okay. So turning to plasmons is another example of where you can look at this this physics. So again, there's a lot of people in this institution and in this room with a great deal of expertise on plasmons, more than I have. But we're looking at, just a specific, we want to look at the specific quantum geometric aspects of things. So nowadays, plasmonics is such a huge field. And a lot of what people do nowadays is actually look at kind of look at the oscillations of the electrons against the positive ionizing background in terms of electric fields and currents. It's basically, in some sense, in terms of macroscopic quantities. However, for us, we want to think about quantum geometric properties, and we're allowed to do this because the plasmons are, after all, kind of the low-lying basic quantum excitations of the metal as well. And they have a Hilbert space, and they can be and are parameterized by wave vector in a system that has translational symmetry. All right, so we should, in principle, be able to think about quantum geometric properties in this system. Okay. So again, we're going to go to the simplest Hamiltonian you can think of, which is just a band structure. Again, just a gapped Dirac point. If you go to very sort of small chemical potential, so now we want to have chemical potential out of the gap. if we want to talk about plasmons. If we go near the band bottom, for example, but not all the way down, you can write down a very simple, again, quadratic approximation for the energy. And in fact, very generally, you can compute the Barry's curvature for this band structure. This is kind of a homework problem that you can give in condensed, which I do give in condensed matter physics when I teach it. But another point is that, again, when you're kind of looking down near the bottom of the band, you can say that the Barry's curvature becomes approximately flat. Okay. All right. Another point is this parameter here is very important. This basically this ratio of delta over v squared. This is going to end up kind of, or it's really v squared over delta squared is going to kind of characterize the strength of the Barry's curvature in the system. Okay, so we want to look at quantum geometry. We need some wave functions. There's a very nice way to do this that goes way back in the literature, way back even to the 1950s, where you formulate your plasmon wave functions by looking for a raising operator, a ladder operator for the Hamiltonian. And so you write down this general form for a ladder operator, and write your Q here, your raising operator, in terms of particle hole. So destroying a particle below the Fermi surface and raising it to above the Fermi surface, right? So it becomes a linear combination of particle hole pairs. Okay, and it turns out that if you make an RPA approximation, that you can actually compute these coefficients almost analytically. Actually, really, if you do the system when it's translation invariant, you can do it analytically, and thereby have explicit wave functions for the plasmon states. Okay, so that's very helpful for us. Okay, so again, this is kind of one way of writing down those plasmon wave functions. They have these factors here, indicating which states are filled and which states are empty. That's sort of important. Our particle hole pairs are now across a Fermi surface rather than across a gap. Okay, but nevertheless, ultimately, your wave functions are linear combinations of these tensor products of states below or above the Fermi surface in this case. Okay, so excuse me. So here we have a representation of this wave function, kind of in two different levels, limits. One where the Barry's curvature, we take a limit where the Barry's curvature goes away. This is being shown as a function of the difference coordinate between the electron and the hole. And the important point here is to notice that it's centered at r equals 0. Right? So that this is saying that the oscillations of the plasmon actually are kind of symmetric around, basically symmetric around the center point of your particle and your hole. Right? Whereas in the gap Dirac case, you discover that those oscillations are not around r equals 0. This is indicating that your plasmon kind of has a permanent dipole moment to it, a permanent electric dipole moment. Right? So we're used to thinking of plasmons as an oscillating dipole moment, but we see in these situations that, of course, that oscillation is there, but it's actually oscillating around a non-zero time, a non-zero time average of this dipole moment. Okay. All right. So this is present. We can compute it in sort of our formalism. And this actually turns out to be something that you can do. Again, this is at long wavelengths. So this is when the momentum of your plasmon is small. You can actually compute this analytically. And here's that parameter, v squared over delta squared, which characterizes the Barry's curvature, and we see ends up being rather important. If this went to 0, this dipole moment will also go to 0. So we seem to need to have the Barry's curvature present at the same time if we want to have one of these dipole moments in the plasmon system. Okay. All right, so this is just another representation of, it's a derivative of that wave function that I showed you, showing again that this dipole moment is present. All right. So we wanted to think about, how would you know if a plasmon has a dipole moment like this? And one hint for this is to think, so we came to thinking about scattering of a plasmon off of a charged impurity. the possibility then came up that this could be a system that hosts skew scattering. And there's a hint for this possibility of skew scattering if you just kind of look at this most simple-minded way of thinking about what scattering does. And that is to kind of look at an impurity that's kind of small compared to the size of the dipole moment, if you like, of your plasmon, so that you can make kind of a very simple approximation for the impurity potential. And then we have wave functions for our plasmons, and we can just carry out a Born approximation to look at the scattering by that potential from one momentum to another. And so when you use this simple form for the scattering potential, you discover that the scattering amplitude is proportional to this dipole moment. Okay, so you get skew scattering when you have this kind of dipole moment in your plasmon. Okay. Okay, so that was very nice, but we recognize that there is a problem here, because this in the Born approximation is the answer. And in particular, it doesn't have any forward scattering at all. This says that if the scattering wave vector and the incoming wave vector are the same, this vanishes. Right, and that's a problem, right? You would expect there to be some forward scattering as well. And the problem, it turned out, is that this very simple approximation, it only looks at the scattering of the plasmon from the impurity potential itself, but the impurity does more than this. The impurity actually changes the density of the ground state, and we weren't taking that into account. So this turns out to be a lot more work to deal with this. We ended up coming up with a couple of three different ways, actually, of sort of analyzing the situation. There's kind of an RPA, and this is one which I'll tell you about a little bit more. This is sort of RPA where you completely include the effect of the impurity, all of its effects to linear order, to first order in the impurity potential, including that screening charge that builds up around the impurity. And then you can actually do other kinds of analyses that sort of in both cases are kind of a macroscopic analysis. They both sort of involve how the electric fields and currents are changed by the presence of this non-uniform density in the ground state. And they basically all give the same result. So I actually want to kind of focus on the first one, the RPA approach, because it gives us kind of a rigorous result. So the idea here is that we look at this raising operator, which I was able to, as I said, compute analytically in the case where the system is uniform. But now if I have an impurity potential, there's going to be a correction to first order in the impurity potential to this raising operator, in which if we have an incoming wave vector k0, we can now scatter into any of the other wave vectors. Okay. And so now we could write down an effective bosonic Hamiltonian for the system would be kind of this Q dagger K0, Q dagger K0 summed over the K0s. But now we see that we're going to get some mixing of different momenta through the Q1, so possibly scattering into other momenta. Okay, even in our simple bosonic Hamiltonian. And we can now treat this as our scattering Hamiltonian. And the idea here now is, now I've got the scattering Hamiltonian, I'll use this as my perturbation for the Born. So we can calculate then a scattering amplitude. It's kind of a long calculation. It's somewhat involved, but there is a limit, a useful limit, where you can get results that are kind of nice and easy to interpret. So what you find in general is that the result breaks up into three terms. Whoops, that's a blank slide. And if you look at the limit where the momentum transfer, so the change in momentum from incoming to outgoing is small, when that's the smallest momentum scale in the problem, we can write down these three contributions in very simple forms. So the first one turns out to be just exactly what I described from the direct scattering from the impurity potential. It's the Born approximation if you just take into account the impurity potential itself. As we said, that gives us skew scattering. There's another piece which comes from, again, it already comes from the induced charge, and this gives us that forward scattering that was missing in the previous simpler analysis. Okay, so this actually does not go to zero when delta k goes to zero. That's the part we knew we need to have somewhere. The last part, it turns out, is an enhancement of the skew scattering. What we find is this is also coming from the induced charge in the ground state. It's proportional to this Born approximation piece, but in the limit where the delta k gets very small, this coefficient actually can be bigger, basically much bigger than 1. And so that's rather when the k gets small, not the delta k, but when the momentum itself gets small, then this coefficient can become bigger than 1 and actually dominate the scattering. And that's sort of interesting because what we recognize here then is that the parts that have the skew scattering here and here are proportional to this quantum geometric dipole. So this is telling us that if you can observe any change in the scattering amplitude as delta k goes from positive to negative, you know you have a quantum geometric dipole in your plasmon. Okay, so this is kind of a rigorous observation you can make, which will tell you yes or no, do I have a dipole moment in my plasmon? Okay, so I have. Okay, so let me just say a little bit more about this other approach. The one thing that was nice about that approach that I just described is it gave us a rigorous result, but it really only works for delta k very small. I can only write down something simple for delta k very small. And if you want to actually like measure skew scattering, you want to know how the scattering behaves as a function of angle. And so you can look at that in a different way using a macroscopic approach. Here the idea is that we're really going to take into account the density being in the ground state now being a function of position because of the impurity, and basically adopt a kind of local density approximation for the Hall conductivity of the system. And that lets you make a lot of progress, it turns out, when you make this approximation, right? So we discussed this before. There's a Hall conductivity associated with this kind of gapped Dirac point. All right. So the simplest way to look at this is just to take some basic relations here. So we have some density modulation because we have density oscillation because of the plasmon. And then you use basic relations here, right? The Poisson relation is going to give us some potential. That potential defines an electric field, which gives some current. And then the continuity equation connects everything back together. You want to actually solve this self-consistently with this Hall conductivity that's not uniform. That's the part that becomes non-trivial. Okay. Okay, but indeed this gives you, once again, gives you the skew scattering. So the thing that, the quantity that's nice to look at in this context is the potential that's induced because of the plasmon. It has a plane wave piece. That's just what you get if you didn't have the impurity potential. And then you have a part that is circular scattering with a scattering amplitude. It's not circularly symmetric. It's a function of the scattering angle. Okay, and you're able to actually compute what that amplitude is, okay, and within this approximation. And once again, this part over here you see is anti-symmetric with respect to theta going from positive to negative values. That's the anti-symmetric part that gives you the skew scattering. So again, this has the skew scattering, but what's nice about this is now we have the full range of thetas. We could ask what would happen if you could set up some kind of experiment where you measure around the impurity what the scattering profile looks like. So a kind of experiment you could think about would be ones that you get in scanning near field microscopy. So here you have like an antenna, some laser exciting your antenna, ends up exciting plasmons into, this is supposed to be, I guess, a representation of graphene, although you need it to be gapped to actually get this. In any case, we can have our plasmon coming up towards impurities that would, from which we'd get the wave scattering. And then if you have a tip that's near one of these impurities, or it could just be an island that you made, a charged island that you made if you don't want to use real impurities. Either case, behind here, if you scan behind, you should see a difference in the left and right, sort of in the scattering intensity when you go from the left or right side of the impurity. So that would be the skew scattering itself. So in principle, that's something that should be observable. Another type of experiment that we thought about, and we just sort of finished analyzing, this just came out actually a few weeks ago, a situation if you have a quantum wire or some kind of nanoribbon or something like this, where you actually confine your plasmon to a quasi one-dimensional region. So there you might imagine, and we actually showed that you can get a dipole moment that's transverse to the wire itself, transverse to the momentum. And now if you set up an electric field that's perpendicular to that dipole moment, you could actually change the energy of your plasmon. And in these 1D settings, the plasmon actually essentially move with a velocity. The dispersion is essentially linear in K. The energy is linear in K, and so there's some velocity that the plasmon will move with. And with an external electric field, you could change that velocity. So this is a way of seeing that the system actually has a dipole, that the excitation has a dipole moment. Finally, I need to say something over here that in order to see any of this, we have to break time reversal symmetry in some way, right? We can't have two valleys that are sort of symmetric or they'll just cancel against one another. So you can imagine, for example, if this was a TMD, maybe you could put in a weak magnetic field rather that would imbalance the two valleys and allow, again, the plasmons to have this dipole moment associated with them. There are other kinds of geometries you can think about where this kind of physics should be able to come in. All right, so there's my summary slide. I've told you about a new quantity that we're interested in, this quantum geometric dipole. It's something that we see in collective mode wave functions. And I talked about a few applications here. It's relevant in the semi-classical dynamics of the excitons and in scattering of plasmons by density and homogeneities. Again, here's a few papers where we report the results. So thank you for your attention.